light years. And values have been very diverse. I mean, for example, one value I think was 50 kilometers per second per megaparsec, and that was rather low. And a low value of the Hubble constant indicates that the universe is old, with the expansion been going on for a long time, and a higher value indicates that the universe is much younger. Now, these new determinations from M100 seem to indicate that the real value is something like 80 kilometers per second per megaparsec. That's higher than has been believed, therefore the universe is younger, and that does cause problems. But how sure can you be that these new determinations are correct?
Well, we basically can use two methods to derive h0 from distance to M100. The first is the very simple method of simply dividing the precession velocity of the Virgo cluster by the distance to M100. The problem with this is that because the Virgo cluster is very populous, as you see here, it's almost covered with galaxies, the peculiar motions are rather high. And so that adds a rather large uncertainty on the value. But in any case, the value we get is around 80. However, we can reduce that uncertainty by using the distance to M100 to calibrate secondary distance indicators. Now, these secondary distance indicators are a way of determining distances to galaxies well beyond Virgo by using such properties as by measuring the velocities within a galaxy to measure its total mass and hence its total luminosity, or by measuring individual bright objects within the galaxy, which gives us its total luminosity and hence this distance. Now, the thing about these secondary distance indicators is that they all seem to agree. They all give the correct relative distances to galaxies beyond Virgo. The problem has been we haven't got a good calibration for these. So we can use the distance to M100 as a good indicator of the distance to Virgo and hence calibrate these secondary distance indicators. Now, in the days of Hubble, he was able to measure the distances to about a dozen galaxies and measure which went out to distances that had velocities around 1,000 kilometers per second. These secondary distance indicators allow us to go out to velocities well beyond that and up to distances of over 10,000 kilometers per second. What we're aiming to do is to calibrate these secondary distance indicators with the M100 distance, and that also gives us a value of around 80 kilometers per second per megaparsec. But because the Virgo cluster is rather extended, we're not very certain of the distance to the Virgo cluster itself. So the actual value of h0 lies somewhere between 50 and 100 kilometers per second per megaparsec, but the most likely value is 80.
Well, it all seems to fit, doesn't it? But let's turn now, can we, to the ages of the stars. And here we have at least something to guide us, because we know the age of the Earth fairly precisely. It's about 4.6 thousand million years, and since the planets were formed from a cloud of material around the Sun, clearly the Sun is older than that. And yet, we are fairly sure that there are many stars which are much older than the Sun.
Yes, that's true. Stellar evolution tells us that metals heavier than lithium had to have been produced in stars. And in the Sun, we can observe these more massive metals. And on the Earth, we can mine such useful elements as iron and carbon and silicon, for which we can build useful things such as telescopes. That tells us that the Sun and the solar system had to have been produced by at least one generation of previous stars. Now, a star of about the Sun's mass will eventually become a red giant and form a planetary nebula. Here's a very famous picture of the Helix Nebula taken by David Malin. And more massive stars in the Sun will eventually become supernovae. One such star is in the Carina Nebula, which is about 50 solar masses. It will certainly become a supernova, and when it does, you'll see the remnant, and here's a picture of the Crab Nebula, and a similar picture remnant is the Vela Nebula. From these supernova explosions, the metals produced in those will then recondense into stars, from which presumably the Sun had formed. However, there are also other stars in our galaxy which are believed to be even older than the Sun and are at least around 14,000 million years old.
Well, that's all very curious indeed. Do you think there's any chance that our estimates of stellar ages are completely wrong?
Well, it's certainly true that we cannot completely describe the nearest star being our Sun. For the most obvious example being the paucity of solar neutrinos. These are produced in the nuclear reactions in the very center of the Sun, and there are too few to agree with the current theories. However, if you talk to a stellar evolutionist, they'll tell you that the lowest age that they can put on the oldest stars in our galaxy is around about 12,000 million years. And this is in fact still older than the age of the universe determined by H0, which is around about 8,000 million years, which puts us back, in other words, the ages of the stars are still older than the Big Bang.
So we have a problem. It seems that either our estimates of the ages of the stars are wrong, or else we're wrong in giving the Hubble constant a value of something like 80 kilometers per second per megapascal. They can't both be right. What do you think is the answer, Sean?
Well, I suspect the answer lies in the theory of the Big Bang itself. Although theorists like to have a high density of the universe, observationally there's no evidence for it. And if you plot the allowed values of H0 and the allowed values of the density, you get a box that looks a bit like this. H0 ranging from 70 to 100 and the density from 0.1 to 1. Now, if you put up the lowest age of the oldest star in our galaxy, you can see that the two areas intersect at a low density. So that's one solution. Alternatively, we could go back to Einstein's original theory and introduce the cosmological constant, which would then allow us to have both a high density universe, a high value for H0 and old age.
Well, it's a fascinating problem. On the one hand, we have evidence that some stars are more than 14,000 million years old. On another, the universe can't be more than 12,000 million years old. And quite clearly, something is wrong somewhere. I'm quite sure we're going to solve it before very long. But meanwhile, I think it's fair to say that cosmology is in something of a crisis. Sean, thank you very much. Now, don't forget, it's newsletter time. If you want the latest newsletter, then send your stamped addressed envelope to newsletter number 56, The Sky at Night, BBC TV, London W12 7TS, or of course CFAX page 615, or you can dial up the Sky at Night information line 0891 800 330. When I come back next month, we're going to return to the solar system and talk about those fascinating new objects right from the Kuiper belt. Good night.